2- and 3-dimensional kinematics are not all that different from 1-dimensional. If you understand the reasoning behind the 1-dimensional case, dealing with more dimensions is fairly straightforward. We deal with each dimension separately, essentially turning a 2- or 3-dimensional problem into 2 or 3 connected 1-dimensional problems. You can see here how this 2-dimensional situation can be split up into 2 separate types of motion, one in the x and one in the y direction. This is where vectors come in real handy, so if you haven't already done so, and you don't yet feel comfortable with vectors, I would suggest watching my vector overview video. Also, being able to keep track of the different terms and what they mean is very important from here on out. So I would also suggest watching the beginning of my 1D kinematics video, if needed for a detailed description of those. Since we will be dealing with more dimensions, we will more concretely deal with displacement, velocity, and acceleration as vectors. Each can be broken up into separate components for each spatial dimension. Every vector is going to be made of an x component, a y component, and a z component. Though, most of the time in this section, our vectors will effectively only have an x and a y component. They will be 2-dimensional. One convenient way to deal with labeling, which I will be adopting, is to call displacement r, velocity v, and acceleration a. Then, when we want to talk about one dimension at a time, we add a little subscript denoting the component we are dealing with. Thinking back to 1-dimensional kinematics, we were able to find certain values, positions, velocities, accelerations, and times, using the kinematics equations. The same will be true in multiple dimensions, except the different components must be dealt with separately. The equations then become something like this, where each equation has only variables of the same component. This is why each of the vectors is broken down into components, because each dimension is independent of the others. They are broken up to find how much of a certain vector is in the x, y, or z direction. In other words, the components of a vector are the amount of that vector parallel to a certain direction. For example, the x component of this vector here, which doesn't have to be velocity, would be the same as the horizontal length of the vector. If we were to box this vector in with 2 vertical lines on either side, the x component would be the same magnitude as the distance between the lines. The same would be true of the y component, but instead with horizontal lines. Solving for the components numerically, trigonometry is used. The animation that you saw at the beginning of the video shows a nice way of looking at how the dimensions behave separately. The spheres moving on the x and y axes show what each dimension is doing independently. Only when the dimensions are added together do they resemble the motion of an object moving in a circle. A simple demonstration shows the independence of each dimension. 2 balls fall from the same height. One is dropped, the other is launched horizontally at the same instant. Which one hits the ground first? They hit the ground at the same time, and maintain the same vertical height during the entire fall. This is because both start off with an initial vertical velocity of 0. Even though the one that is thrown has an initial velocity, this velocity is only in the horizontal direction, which does not affect motion in the vertical direction, so they hit the ground at the same time. Now, how do we deal with vectors in application? First, a small disclaimer. I will often deal with quantitative problems using only variables. This is because doing so can help with physical reasoning skills, highlighting how different quantities are related and used. This may be difficult at first, but will make things easier down the road, so I urge you to follow along and do your best. That said, let's look at the situation we were just talking about, but only focus on the launched ball. Let's say we know the initial velocity of the ball, and the height it is dropped from, and we want to find the distance the ball travels in the horizontal direction, also known as the range of the ball. First we ask, what is it that we know about this situation? We know the height it was dropped from, which we set equal to ry initial, and the starting horizontal position we set equal to 0. We know the initial velocity is given, so we just need to split this up into its component parts. In this case, we can do this simply by looking at the situation. The ball is launched completely horizontally, meaning it has no vertical component at the start. So Vx initial is equal to V initial, and Vy initial is equal to 0. Finally, we assume this is taking place on Earth, which is a fair assumption to make unless the situation is stated to be otherwise. That means we are in the presence of a gravitational acceleration, g, in the downward direction. Because we are neglecting air resistance, as we do, there is no acceleration in the horizontal direction. Now we look at what we don't know. We don't know the range of the ball, which is what we are trying to find. We also don't know the time it takes the ball to fall to the ground, or the final velocity of the ball. So now we ask, how are we going to get to what we want from what we know? Analyzing the situation, we see there is no acceleration in the x direction, which means the velocity in the x direction is constant. So we can simply multiply the time the ball is in the air by the horizontal velocity to get the range. Oh, but we don't know the amount of time it's in the air. Well, there's no other way to find the range of the object, so can we find the time? Yes, we can, but we have to turn our attention to the second dimension. Like I said earlier in the video, focusing our attention on just the vertical dimension turns this into a problem where a ball is dropped from a certain height, since they fall at the same rate in both cases. This is easier to deal with, and using the information we have, we should be able to find the time it takes for the ball to hit the ground. Looking at our kinematics equations, we don't have the final velocity and we don't need to find it, so we eliminate all equations using it. That leaves us with this equation to solve for time. A little rearranging and we are able to find the time the ball is in the air, meaning it is traveling at its constant horizontal speed for the same amount of time. Now we simply multiply these quantities together to obtain our range. And that's it. If we are given actual numbers, we could plug those in, but the reasoning remains the same. I appreciate you taking the time to watch this video. Please like, share, and subscribe to support my channel. And if you feel you are able, and that these videos are worth it, you can support me through Patreon, crypto, or PayPal. Links in the description.